My name's Yong Tian. I'm the Director of Product Management for MemVerge. And today I'll talk a little bit about our Big Memory Workbench. And it is specifically designed for data science involving big data as well as AI applications. So first, what is Big Memory Workbench? We view it as a set of solutions that takes the transparent memory service that Yue has just talked about, that's built into our memory machine, and then applies it to the data science workload. And specifically, it includes like user applications with our memory machine running on top of our memory machine, as well as a set of interfaces to both allow the end user and the applications to interact with the memory machine. We would run on hardware that includes DRAM, PMEM, or we could just run on hardware with DRAM as well. The workload that we have designed for is two characteristics. One is large memory. When I say large, I mean typically our customers come to us for jobs that's in the hundreds of gigabytes up to a few terabytes of data. Also computationally intensive. We handle workloads that runs for hours to days to weeks. We just finished one that ran for 3 weeks. So these are kind of like, these are the characteristics of the workload. And then we have seen workload in machine learning, AI, bioinformatics, financial, the more traditional scientific computing, as well as like business intelligence. By the way, feel free to stop me anytime. So our kind of motivation for this, I think like these are the pain points that we have heard from our customers. I'd love to see how or whether it resonates with what you guys see. I think fundamentally there's two issues, and then it shows up in different ways. The two issues is it's data bigger than memory. I think in the past few years, the data growth has definitely grown faster than the DRAM's ability, both in terms of density as well as in terms of cost. So when you have these large jobs, what do? I mean, like the most direct way, you buy more DRAM. That's getting more expensive, actually. Unlike other microchips, the DRAM price is actually going up. You could also do more splicing up the data into smaller slices and processing in a distributed manner, like MapReduce. But that would involve pretty expensive and software effort, particularly if you don't have a good framework already in place. And then like lastly, probably other solution is that you can downsample and then run it with a smaller memory, but that will give you inferior results. So these are kind of like that's on the data bigger than memory side. The other issue is the computation intensive, and I think like we see this in AI, we see this in bioinformatics. It's you have jobs that runs for hours, days, and weeks, and because of this long execution time, there's a heightened risk of data loss. Somebody unplugs a computer, boom, your work for the last week is gone. And we actually had seen this happen. Like the solution to this is checkpointing, right? So people traditionally people checkpoint based on file system. And then for those solutions, what happens is one is that, again, you need some software development to enable those solutions. And second is this overhead associated with the checkpointing, especially like when you flush like gigabytes of data from memory to a hard drive. Even on SSDs, I mean, we have seen 20 minutes up to like maybe like an hour and a half for just storing the data from memory to hard drive. So even if you have checkpointing, you may not may not be regularly used just because of overhead. And then because of all these things, like, it's a lower efficiency, right? As I think we had shown for art and entertainment, people, scientists or data scientists working on these algorithms, they don't want to be interrupted in this workflow because of the checkpointing. So these are the issues that we see. And then how do we handle them, right? So with Big Memory Workbench, that's our value proposition. That's our job to make this pain point go away or make it easier. First, on the memory side, we work with DRAM plus Intel Octane, and then convert that into one single large consolidated memory space. So you can access it as a one memory space without any application changes. I think I jotted down this note here. I think Mark had a question about what is our advantage compared to Intel's App Direct mode. I would say, like, at the first shot, what we do is we enable your current applications to run on this large single memory without any modifications. And then compared to the other mode where Intel has the memory mode, we enable persistence, and we actually free up the DRAM to be used as a memory rather than as a cache. So, that's at the first level. At the second level, of course, we have all these additional services that we can provide on top. I mean, like, we love Intel. Intel is our big investor. What we see is that we can fill the gap that the Intel solutions have right now, and then being able to help our end customers. I think so. That's like, let's talk about some numbers. Like on a single server, we can support up to 8 terabyte of memory. So this is assuming a 2-socket server, 8 terabyte of memory. And then we actually have people that uses that much memory. Using PMEM, again, like because it is a denser medium, cheaper to produce, we can save up to 30 to 50% in cost saving, depending on the ratio, right? I think there was a question earlier about the ratio of PMEM to DRAM. So this is how we can tackle the data bigger than memory issue, and I'll have some examples later on. Second is, as maybe this is a little bit reiteration of our snapshot restore service that just talked about. It's a zero IO in-memory snapshot. Compared to the file-based snapshot, we have minimal performance and memory overhead. So, instead of doing tens of minutes to hours, we do it sub 1 second. We can do all these things. And then we have integrated cloning, migration features that build in. And finally, I want to say this is, in order to use all these capabilities, you can just take your existing application, take it, and then just run on top of Memory Workbench without any change. Now, the caveat is that if you want to take full advantage of this, then you may have to do like 1 or 2 lines of change in order to do that. I'll show you some example of it.
Again, I have a bit of a security background. So my question is, with these in-memory snapshots, if a bad actor could exfiltrate that snapshot, is that useful? Can it be exploited? I mean, obviously they'd have to have your software on their own server to load it into memory, but is that possible? Or when CXL comes in, will that be possible?
That is a great question. I think, do you want to take our security architecture question?
So, Josh, are you asking about analyzing the snapshots for security analysis, or is that?
Yeah, if I'm taking, I've got a Redis database in memory, right? Right. And I take a snapshot of that. Mm-hmm. And a bad actor comes along and they're able to get access to all those snapshots that exist on PMEM.
Yes.
Right. And they exfiltrate that and they put it on their system. And they could theoretically have my Redis database, right?
Yes, yes. So that's true. So, but basically, this is basically you can if the snapshots in memory, the memory it depends on how secure your environment is, right? So the PMAN today also actually enables the encryption features. You can prevent you from getting those snapshots. So and also if you export our snapshot to storage, the storage has a security features that prevents a hacker from getting that. Yeah. So I think our security assumption is really based on the hardware security. The security assumption based for PMAM and for your storage system and for your OS.
Yeah, I just from a security posture point of view, this introduces a new vector that I don't think cybersecurity professionals had ever considered before. Oh, suddenly I have a snapshot of what was in my memory on this machine. That to me is kind of big.
Yeah, and for sure, we'll definitely will also provide the decryption features for snapshot in memory as well. Yeah.
See, now that's nice.
Mm-hmm. Yeah, so maybe to reiterate the comment for Josh is so we provide our own security for the snapshot, and then on top of it, we actually depend on your entire system security. So there's like 2 levels involved there.
Right. Security is all about the layers, right? So
yeah.
Understood.
Okay, so I'll move to the next slide. This slide just kind of, I think you might have gone over this previously as well. I just want to show you the interfaces between our memory machine as well as the applications and in users that's using it. You can see here we have a GUI, we have a graphic user interface. This is actually our studio interface, and then we have an icon here. If you press it once, it brings up like the previous snapshot that have been taken. You have an option to comment on it or restore it from here. We also have different settings. So instead of like manually taking a snapshot, you can have an autosave feature like every 5 minutes, 15 minutes, half hour to save it. That's more for kind of the data loss recovery.
Yeah. Are you doing this with RStudio Desktop or the RStudio Server and Connect products for that central server experience?
We can do it with both. So with a desktop, it's a widget that's running on the machine. We also have a web version of this it's essentially a widget running on the local machine, but it talks to our server by REST API, and then that client, our memory machine agent, will be sitting on the same server that RStudio sits on.
And in that server instance, how does the widget get injected into the RStudio web client interface? Or is it like an add-in, or how would a person logged in with their Active Directory be writing some code, hit that button to snapshot memory?
Yeah, so I think right now our widget is in production for the local machine. The way we envision it being used is that the widget will still be running on the local machine, but the widget talks in the backend by REST API to our memory agent on the server. And then when in order to log in, the first version of this, there would be some login security feature in order to access the memory agent. So as a user, they may have to log in twice. The first time to log into the RStudio server, and then the second time to log into our memory machine.
Okay, so you see it more as a centrally deployable widget out onto people's devices where they'll have control over memory snapshotting on the central servers with MemVerge installed.
That's correct. And then, we're always taking feedback from our users. We're a startup, so we deploy fast and then, iterate fast. So that's, And I mean, I love to hear your feedback on this kind of application architecture as well. And then like with a widget, it's really easy. You can take double click on this icon and then take a snapshot manually. We also, I think, as you have mentioned, we support the command line interface. So I have a few examples here. This is actually the command for, I don't know if you guys can see my cursor, but the first line is the command line to take a snapshot. Second one is to list the snapshot that has already been taken. And then the last one is to restore the snapshot. We have a REST version of the command line as well. So as far as application, what you could do, like let's say in R code, you could wrap the REST API for taking a snapshot inside the code as well. So you can you can programmatically take the snapshot using that wrapper. We have the documentation for our REST API if you're interested. I don't show it here because our REST API always works. It never takes a break, so I can't drag it to the meeting. That was a joke. My kids kind of laughed, but anyway. Any questions here? Okay. Next slide is I wanted to talk about some use cases, how we were able to use this benchmark with our customer. The first one is from single cell RNA sequencing, and the particular use case is like a characterization of mouse cells. I show this pipeline here on the left side because I think even though this example is from genomics or bioinformatics world, but there's some similarity between AI and this pipeline, the AI pipeline stage, and this one. So first of all, like when people looking at this RNA sequence, they do quality control, like get rid of the noises, take out the bad data. Then they do normalization, making sure like all these like what they call like a cell count matrix are kind of equivalent, like they're maybe taking out some of the boundary conditions. Then they do feature selection, feature engineering, that to dimension reduction to kind of further reduce the complexity involved in a large data set, so we can analyze the ones that matter. So I mean, like use PCA, principal component analysis, at this step to reduce the dimensions. Then then this is a part around like the clustering analysis. For this particular case, it's actually going from quality control to clustering, and it is a 11-stage pipeline. It shows up linearly here, but there's a lot of loop back from one stage to previous stage or the previous two stages to tune parameters or for debugging purpose. And then because of this kind of a parameter tuning, people, even before we got involved, they were doing saving to a file. So it is a checkpointing in the sense, but it was saving the data to a file. And about 60% of the time when we analyze it is actually on the I/O. It's spent on the I/O from either save the file or load the file later into memory. When we replaced the file saving with a zero I/O memory shot, zero I/O in memory snapshot, what we were able to do is we were able to reduce the execution time from 6.5 hours to about 2.5 hours. And then you can see here is kind of like this is the baseline, and then this is what the orangey one is what we were able to do for the execution time of each one of those stages. Some of the stages are, like stage one is really compute intensive. So we were able to reduce some of the time, but not a whole lot. But let's say like stage 4 and 5, where they had a lot of these iterative analysis. So we were able to reduce it quite significantly because of this I/O time.
So sorry if I missed this, but is it basically almost every time there was a read or a write file command inside their process, instead you said load snapshot or create snapshot,
Yep.
and that's the level of intensiveness of change that's needed.
Yeah, that's the exact point. Yep. Yeah, so that's why I say like we say like no application change, but there's a little bit of caveat. Is like if you do this thing with our manual GUI, then that's true. There's no application change. But if you want to make your life a little bit easier, then you can use the REST API as a wrapper to the R code. This was running on R to automate that. Okay. So the second example is coming from the plant genome analysis. It's like a comparative analysis to figure out the kind of the genetic component of how certain traits has developed over many species and subspecies of the plant. So the key here is that the more plants and then the more samples that you run together in this analysis, the better result you get. For this particular case, like the hardware was limited to 500 gigabyte, so they weren't able to run the full set of analysis. As the researcher had some questions they want to answer, and then the bioinformatics team was unable to run the job in order to answer those questions. And what we did was we provided our memory workbench running on top of a system with an Intel PMEM that had aggregate like 1.7 terabyte of data. And we were able to finish this job in a little over 3 weeks of runtime. So the researchers got their answers, and then they're publishing a paper there. Actually, the other caveat I want to add here was the bioinformatics team. I suppose they could have changed the algorithm in order to, divide it up into a distributed node, but there's no time in their workload to do that, and then they didn't have some dedicated software engineer to do the distributed work kind of architecture modification. So the third example is an example from I think it's lung fibrosis research. Again, they're trying to figure out some of the genetic underlying causes. And what's a key here is that the original analysis is single-threaded processing, and we, in essence, the processing itself could be parallelized. It is working on the same set of data, but because of the framework they were using, it was run in a kind of a linear sequential fashion. What we came in, we analyzed all the pipeline stages involved. We figured out which ones could be parallelized, and these are the color-coded ones. So even though they're running sequentially, all the red labeled blocks are like ones that truly needs to be sequential. Like the red and yellow could be running parallel. What we did was at the beginning of this pipeline stage, we took a snapshot. We cloned 4 of these snapshots, and then we just commented out all the code that doesn't need to be run, only running the ones that need to be running a sequence. We were able to basically parallelize a process that took 6, I think like this this entire stage is about 2 hours and 48 minutes. And we were able to complete that in 1 hour and 16 minutes by doing this parallel processing. And the other key thing to note here, I think Yue went over, is that these 4 clone processes were actually using this shared memory to start with. So originally, like the memory is about 140 gigabyte. If you had just cloned 4 of them, it would have been 560. It would have been like a 560 gigabyte. But instead, I think we only took 240 gigabyte of memory to run this. And that's because we're taking a snapshot and then we're saving diffs for each one of these parallel processes.
Is there a way to merge clones? So for example, if you have one vertical that makes a change that the other ones might be waiting for or would require?
Yes, we actually do that. We do that here. Like in this case, like the data from these 4 stages are merged into one for further processing. The way we're merging it now is we're actually writing to file to merge it, because because like if we use our completely in memory part, we probably have to modify the application a little bit more to basically have a block level access to do that. And then like I think our researchers didn't have time to do that part. So we took the easy route in this case. If we do that in memory merging, I think you're going to see like the time saving is going to be a lot more than that 36%.
Right, and then when it's merged, you can return your clones or you destroy your clones, I guess.
Yeah, we do that. Like at the end of the stage, we actually do destroy the clones.
I think you elaborated the value proposition for data scientists and AI folks really well. What are you doing to help make them kind of aware of these things? Is there, how does a data scientist identify they need MemVerge to solve their problems?
That's a great question. I think we're still trying to figure out how. You notice like the 3 examples I have are all from bioinformatics. These are actually 3 different customers. And then like we started off with the first one, like so it was actually chronological order. The first one, the single cell RNA analysis. So far it's been kind of like a word of mouth, like I think like bioinformatics field, people are fairly like academically minded, and then like they talk a lot. So like that's how we found from 1 to 3 customers really quickly. We're still kind of in the branching out phase. Like I think Yue and Frank mentioned earlier, like we definitely think AI and ML is a big field where we can help, and this is where we're coming to. This is our attempt to reach out to the field, and if you have ideas, just general ideas, that doesn't have to be like concrete, specific companies or something. If you have any general ideas, I love to hear them. I think like the thing is, there's so many things we can do. There's so many things that we can do. We need to find the use case. I think on one side people have pain point, on the other hand we have solution. But how do we know about each other? It's we definitely need to do that.
Yong, how's this sold? I mean, it's apparently just all software, right? I mean, the Optane you get from Intel or something like that. And is it licensed on a per terabyte of memory basis, or is it just for the solution itself?
Yeah, so like our software is sold on a subscription basis, and then it is based on like the terabyte or gigabyte, what have you not, that we manage.
Mm-hmm. You don't have any like a free tier, so the first terabyte is free, but after that you have to pay for it or something like that.
Well, that one we have to talk to our sales guy. But yeah, but if that's something that people are asking for, and then like when we work with academic institutions, for instance, we're happy to oblige. Like I think like for us, a lot of it is in the discovery phase. So if anything that we can help, we can bring value to the user. At the same time, it validates some of our assumptions. Then we're happy to figure out some arrangement that works for both sides.
You don't have any special deals for analysts and tech field day representatives and stuff like that?
Send me an email with your contact, your bank number, your password, and then we'll work out the arrangement.
All right, thanks.
Yeah, we are willing to send out the free trials to all the delegates here to test our software.
There you go. That'd be great.
Yeah. See, like, you don't even have to send me your bank account.
But we need the Optane as well. That's the other choice. Well,
that one, like, I think we have a pretty close relationship with Intel has been very supportive of us. So, I mean, if there's some joint project, we can definitely loop Intel into this as well.
Yeah. Meanwhile, if you have a DRAM, we can use actually work for DRAM. As I mentioned, it works for DRAM only as well. Yeah.
That's true. That's true. If it's something that in the cloud or somewhere that doesn't have access to a PMIP, we can support that as well.